In this video, I will talk about the Hall effect. Let us consider we have a slab here or something through which the current flows. Here I have chosen a rectangular slab here, and the current is passing through this rectangular slab along the x direction. So the direction of current is along x axis. And just to make life simpler, we have assumed the charge carriers are positive charge carriers. But if you look at the metallic conductors, the charges are carried by the electrons. But just to make life simpler here, I have assumed the positive charge carriers. But this effect validates even if we consider the charges to be negative. Okay. So as the current is flowing through this direction, all the positive charges are also moving in this direction here. Initially, we have assumed there is no magnetic field. If there is no magnetic field, all the positive charge carriers will be moving along x direction. All right. Now, what happens if we apply the magnetic field? Now I'm going to turn on the magnetic field or apply the magnetic field along y direction. So this is the direction of the magnetic field, okay, along y direction. So along this direction here. As soon as we apply the magnetic field, all the moving charges will experience a magnetic force acting onto it. They will experience magnetic force. The current is moving along x direction. The magnetic field is along y direction, and we already have discussed that the magnetic force is perpendicular to both the velocity and the magnetic field direction. So as the current is along x, magnetic field is along y direction, the magnetic force will be along g direction. So for the positive charge, in this case, it will be along g direction. You can also use the right hand rule here to find out the direction of the magnetic force, or you can use the palm rule here. So in this case, you can clearly see if we, let's use the palm rule here. If the current is moving along this direction, and if you put your fingers along the direction of the magnetic field, then perpendicular to the palm will be along this direction here, will be along g direction. Okay, so we now established that the charges will be moving along x direction as well as along g direction. And as the charges keeps moving along x direction, there will be an accumulation of positive charges onto the top surface here. So this top surface here has an excess of positive charge, and that's what I have shown here. Because this charge will keep moving along the top surface here, so there will be an accumulation of positive charges. As the top charge has an excess of positive charge, the bottom end will have the negative charges here. Okay, so the top surface will have positive charge and the bottom surface will have now negative charge. Now think about here, as the more and more charges keeps accumulating onto this surface, so there will be an electric field from the positive to the negative charge, from positive plate to the negative plate. And this electric field now will, or this electric field, what will the electric field do? It will oppose the positive charges here. So as this charge is now trying to move, this is a positive charge, this positive charge which are now onto the top plate will repel it. So this electric field will now try to oppose the accumulation of the charges. So what does that mean? The magnetic force will try to drive this positive charges onto the onto the upper surface, onto the top edge, the top surface, and the electric field will try to oppose. And this tug of war between the magnetic force and the electric force keeps happening when both field becomes exactly equal. If initially the magnetic force wins, so there will be accumulation of the charge. Initially, as the electric field gains strength, it will oppose, and that will keep opposing till the magnetic force, which is in the upward direction, and the electric force, which is in the downward direction, balances exactly. And at the time, there will be no movement of charges along along g direction, or along the top, or along the top surface here. Okay, now let's exactly do these things mathematically, or derive the mathematical equation. Before that, as there are the accumulation of the charges onto the top surface and the negative charges here at the bottom surface, there will be a potential difference between the top edge and the bottom edge. And this potential difference, or this voltage here, is called the Hall voltage. This is called Hall voltage. All right? Okay. And remember, the direction of this electric field, or the Hall electric field, is always perpendicular to the current and perpendicular to the magnetic field. It is perpendicular to both. Okay. So now, as I mentioned here, the current, at one point, the electric force just balances out the magnetic force. So here is the electric force, and this is the magnetic force here. What is the formula for the electric force? The electric force is given by Q times the electric field. And the magnetic force is given by Q V cross B. V cross B. And here V, the drift velocity and the magnetic field are mutually perpendicular. You see the current is moving in this direction, and the magnetic field is applied along this direction. So they are mutually perpendicular. So in that case, the sine theta is 90 degree, sine theta sine 90 degree will be equal to 1. The general formula for the Lorentz force, or the magnetic force, is Q V cross B, or Q, the magnitude is QV B sine theta. In this case, sine theta is 90 degree. So sine theta here will be exactly equal to 1. So this is simply QVDB. And now electric field. The electric field, this electric field between this top and the bottom surface is given by the potential difference, this potential difference divided by this thickness here, this height. We already have discussed this electric field is equal to V over D. And in this case, the potential difference is VH, and the distance between the upper plate and the bottom plate is D. And we have as it is. This Q and Q cancels out, and the VH is given by this equation. Now this is called the Hall voltage here. Hall voltage here. Now, we already have discussed in the previous chapter the drift velocity. The formula for the current is given by this equation, where the Vd is the drift velocity. Just to remind you, the drift velocity is the average velocity with which the charge carriers move in a metallic conductor. It is the average velocity. So if I look at this equation, then I can solve for the drift velocity. So the drift velocity is I N Q A. And what is N? The N is the charge carrier density, which is the number of charges per unit volume. And A, that's the most significant point here. A is the cross-sectional area. And if you look at this picture here, what is the cross-sectional area here? We have so many cross-section area here. Which cross-section area will be taken into account? The answer is the current is moving along x-axis. So the cross-sectional area will be in YZ plane. So this is my cross-sectional area. And how do we find out the cross-sectional area? The length. So this is the thickness here, T, and this distance is D. So the cross-sectional area will be simply equal to D times T. So that's what I have written here. A is the cross-sectional area, which is equal to dt, or we can also write down at TD. It's the same thing. So here A is equal to D times T. It's not the derivative, it's the dt. So now I'm plugging this drift velocity into this equation here. Okay, so VH, instead of drift velocity, I'm writing out this number here, and then I have B and D, which is right here. The D and the D cancels out. Remember now, the D and D cancels out, so we have this equation here. This is the Hall voltage. And again, here I'm reminding you, this Hall voltage is independent of this distance here. Okay, it only depends upon this thickness here, which is along the magnetic field direction. It is not it does not depend upon this thickness. It only depends upon this thickness here. All right, so this is the Hall voltage here, and the Hall voltage is directly proportional to the current, and we can expect it is directly proportional to the current, directly proportional to the magnetic field, but it is inversely proportional to N. And what is N again here? Charge carrier density. And T here, again, the T here is the thickness along the direction of the magnetic field. T is thickness along the direction of magnetic field. All right, so, and there is another term here. I can write down 1 over NQ. This term together, 1 over NQ, is called Hall coefficient here. All right, so this term reduces to this equation here. And then last point I would like to make here is the VS, the Hall voltage. The Hall voltage between these two, the top side and the bottom end, these two surface here. The Hall voltage produced between these two surfaces is inversely proportional to N, the charge carrier density. And if you compare the conductor and semiconductor, the charge carrier density of conductor is greater than the semiconductor here. What does that mean? That means the voltage produced with the same dimension of everything keeping the same, the voltage produced or the Hall voltage for the conductor will be smaller than the semiconductor, or the Hall voltage produced in the semiconductor is greater than the Hall voltage produced in a metallic conductor. So now the last part is, why do we study? What's the application of studying the Hall effect? The one thing that you can do is with the Hall voltage, if you know the Hall voltage here, then we can know, or we can find out what is the charge carrier density, and this quantity is easily measured. Okay, so if you have a multimeter, then you can measure the Hall voltage. So once you know the Hall voltage, then we can solve for IB VH QT, and all this quantity can be measured easily in the lab. So that will give you the charge carrier density. So the Hall voltage is used to find out the charge carrier density of any material. It could be semiconductor or it could be the metal. So this is it from this video, from the Hall voltage, the Hall effect. If you have any questions, write down your questions in the comment section below, and do not forget to like, share and subscribe the channel. Thank you very much.